Hello, I'm going to talk through some centres of mass examples. I'm going to look at four. First one, centre of mass with two rectangles, so just a straightforward composite lamina, finding the centre of mass, and then we're suspending the lamina, need to find the angle. Second one is going to be a framework example, so made up a series of rods. Again, we've got a suspension. Third one will involve a shape with a hole, a triangle and a circle. And the last one, we have got not a full circle but a circle sector, so we have to use one of the slightly odd formulae. So these will all be on the same video, so you can just go and find the example that you think you want, or just watch all of them, of course, absolutely up to you. Right, so this first one, we have got this shape made up of two individual rectangles, two uniform T-shaped laminas, so that means that the mass is equally distributed all the way throughout. Centre of mass of this one at the bottom is just going to be where the lines of symmetry intersect, so of course that's going to be there. Centre of mass of the one at the top will take us to there. Now it's very much like moments in that we look at the effect of the centre of mass of that part of our T-shape, the centre of mass of that part of T-shape, and that will be equivalent to the single mass, the total mass, and of course it's going to be somewhere here. We know it's going to be somewhere here because the shape is symmetrical, so all of these lengths 15, 15. So it's going to be exactly on that line of symmetry, which of course is what we need for B here. So say somewhere there. Again, very much like circular motion, set your origin. I just always tend to go kind of bottom left, up there, up there. That's my kind of X and Y directions. So this distance here from there to there is defined as being X bar. The distance from there up to, sorry, it's going to be up to there, isn't it, is going to be Y bar. So we consider firstly what's going on with A, B, C, H. I know that the mass of that, well, the mass of course is dependent on the area. I've got an area of 30, 40 multiplied by 10. So the area is 400. The centre of mass for that will be at 20, so halfway up there. So it'll be 20 and then 60 plus that 5. So the centre of mass of that will be at 20 and 65. If we do the same thing for this here, D, E, F, G, the area there will be 10 multiplied by 60. So that's 600. And then the centre of mass, again, it's going to be 15 plus 5, so that'll be 20, and halfway up the 60, so that's going to be 20, 30. Now, what you'll see in many, not necessarily our textbook tends not to do it, but exam mark schemes in integral work as well, is that you can organise this in a kind of little table. So I've got all this information here, but a standard way of writing it is to say, okay, the mass or the mass ratio for each of the shapes, and then the horizontal distance and the vertical distance, which I call X and Y there. So we've got our shape A, B, C, H, D, E, F, G, and then we've got the total shape, the T-shape, the entire lamina. So the mass, of course, is proportional to this. So I could write 200, 600, and then indeed 800 as well. However, 400, 600, we're really just looking at the proportions. So I could use 4, 6 and 8, or most simply 2, 3, which makes that 5. And why have I written 8 there? I was adding 400 and 600, and so I should have got 1,000 there. So that means that that will be 2, 3, 2, 3 and 5. Now if I'm looking at the x's, I can just write down my x coordinate there is 20. And in fact, let's go down, because then the y coordinate I've got there is 65. For my second one, the D, E, F, G, the centre of mass is at 20 and 30, and then my total x bar and y bar. So now we've got that, we can use our general formula. So the general form is to say that the overall centre of mass, it's given by the product of the distance with the mass itself, and that is equal to the individual masses multiplied by their centres. And of course, you know, if you've got more shapes, that would just keep going. So I can write the first one, the total 5 multiplied by x bar y bar is equal to m1. So I can just use the values in the table. I've written them down in a way such that I can just copy those down into my mass vector. Again, you'll see some textbooks, some exam mark schemes do it as vectors, some just do it as, first of all, a calculation for x and a calculation for y. I quite like the vector calculation because it means you don't have to do 2 separate calculations. So 5 x bar y bar is equal to, so that'll be 40 plus 60, 100, 130 plus 90, so that's going to be 220. So then x bar y bar, those two both divided by 5, so 20 and 44. So what I've done there, I haven't really kind of looked at what the question was asking, have I? I've just found the centre of mass. It's wanting the centre of mass from the edge of AB. So AB is actually up here at the top. So from the edge of AB, the centre of mass, 26. Well, I know that the total distance there, so if I'm answering part A, the total distance up to AB is 70. I've worked out that the centre of the mass in the y direction is 44 from there to there. So 70 minus 44 is equal to 26 centimetres. And I said I just went ahead and did it from there anyway. I think even if I'd have properly registered that it was AB, I'd probably still go from that bottom left anyway. Do the same every time, and then just look at what it's asking, look at the specific length, and then you can add or subtract as necessary. B, I won't write that down, but we know why. It's essentially just because the shape is symmetrical. The shape is symmetrical, so of course the centre of mass is just going to be the centre of the shape, which will be 15 plus 5 along. Yeah, it says from the edge GF, so just 5 along because it's half of that 10. Okay, now this here. For any single shape, no matter what the shape is, whenever you suspend an object from a particular point, it will always settle. So say the centre of mass, it's going to be about there, isn't it? So it's always going to settle so that that line there is vertical. So you can imagine pinning that there, it'd swing around, it would swing it around, and of course it would settle so that that line is a vertical. Okay, we don't need to draw the shape out, we just draw the line on. So every single time you draw the line from the point at which you're suspending to the centre of mass, okay, I'm going to mark on that that is my vertical line. Find the angle between the edge and AB. So AB is this here, so all we need to look at is finding this angle. So as long as you identify the correct triangle, it is just a really simple bit of trigonometry. I know that that's 26. So all I have to do is figure out this. I know that the centre of mass is 20 along from there to there. That's 7, so this is 13. So if I just draw this triangle out again, I'm working out this angle. I know that is 26. I know that that is 13. So tan of my angle is opposite over adjacent, so I just need to work out inverse tan of 2. 63.4 degrees. Oh, so it just wanted nearest degree. So 63 degrees. Okay, so identify the relevant points, the relative masses, mass ratio, I've called it here. Use the table if you want, but it is very good to organise because you do have quite a lot of numbers to keep track of, and then using a vector method means that we can just pop all the calculations in together. Okay, so moving on. This one here, we have got a framework. So framework, it's either a series of rods joined together, or it might be a piece of wire just moulded into that shape. So these are the distances, 2a and 3a. Each rod has mass m. Okay, right, so if it was a piece of wire, for example, these would not be the same mass, so the mass would be proportional to the length. So that would be a mass of 2a, that would be a mass of 3a, and so on. However, this one here, just everything, all of those wires have got a mass of m. Now, effectively, what that means is that we've got 1, 2, 3, 4, 5, 6 different points. So that would be equivalent to 6 individual point masses on that system. All of those distances are just going to be halfway. They're uniform rods. So it means that that m will just be 3 over 2a. This m here is going to be at 1a, and so on. So this here, it's not particularly tricky. And I mean, look, there's 7 marks here. It's awkward because there are lots of things. There are, how many did I say? 6 points. So there are lots of things to keep track on. So I think absolutely here I would draw a table. We don't need, as we did in the previous example, we possibly had a little bit of working out to do before we went to the table. Here it is straightforward. So I've got my rods A, B, B, C, C, D, D, E, and no, there isn't a DE, it's an AD. And then I've got those 2 individual masses, the 6m and the 2m, and then I've got my total. So I've got my mass, or my mass ratio. So I could write it as m, 6m and 2m, but I know that in any calculation all of the m's would just cancel. So let's just go with 1, 1, 1, 1, 1, 6, 2, add those up, 12. Okay, so m, 6m, 2m, 12m, all the m's would cancel, so we don't need to bother writing those. So if I look at AB, so I'm going to set this here as being my origin. So the x value is 0 and the y value is just a. I'm going up half of that way there. So 0 and a. BC, I've gone half there, so that'll be 3 over 2a, and I'm going up to the top there, so that's the full 2a, isn't it? C to D, here, I've gone the full 3a in the x direction, but I'm only going up half that, so that's a in that direction. A to D, I've gone along 3 over 2a, but I'm at a y value of 0. The 6m is at 3a, 2a. The 2m is at 3a, 0. And the overall centre of mass, just put it there. You don't have to represent it on the diagram, but that, of course, is x bar. That is going to be y bar. Okay, and then we can just use our vector calculation. I know that the sum of all of the masses, so 1 multiplied by 0a plus 1 multiplied by 3 over 2a and 2a. So I'm just adding up the product of all of the masses with the centre of masses. 1 multiplied by 3 over 2a and 0. Now on the slightly more interesting one, 6, 3a and 2a. I've got 2, 3a and 0, and then finally that is equal to 12 x bar, y bar. 3 over 2, another 3 over 2, so that makes 3, 4, 5, 6, plus 12, plus 18. So I've got 30a. On the bottom I've got 2, 3, 15. I think I missed off that, didn't I? 1, 2, 3, 4, plus 12, 16, yes. 16a, and that is equal to 12 x bar, y bar. So x bar is equal to 30 over 12, so that's 5a over 2, and y bar is 16a over 12, 16 over 12, that's 4a over 3. Okay, so again, I've just kind of done my calculation. I haven't really looked at what it wants. So from AB, so part 1 is that one there. And from AD, yes, from the bottom, so that one is indeed part 2. And then on to B. Again, all we have to think is, so here is my shape. Centre of mass there. I'm hanging it from point B, which is there. So if I was hanging it there, so imagine that swinging away, let's put it on the right point, swinging away, it's going to settle. We just know intuitively, don't we? It's going to settle so that that is vertical. Okay, so I don't even know need to do the whole swinging piece of paper. I just know I'm going to draw that line. That is my vertical. It looks as if it goes through that corner, but of course that isn't the case necessarily. The important distance is from BC. BC is this length here. So that's my triangle. This is my angle. X bar, 5a over 2. Now y bar, so what I've worked out is that distance there at 4/3 a. This is 2a, so this will be 2a over 3. So I know that tan of the angle is 2a over 3 over 5a over 2. 2/15, 4/15, the a's cancel. So theta inverse tan of 4/15, which gives me 14.9 degrees. Okay, so finding the angle, really straightforward. You just draw that line and it's just a straightforward inverse tan to find your particular angle. Okay, next one. A shape with a hole. Exactly the same idea as if you were working out the area of a shape. You would work out the area of the triangle and then you just subtract the hole. What we need to do here is to say, okay, that the centre of mass of that triangle with the hole would be equivalent to the centre of mass of the triangle minus the centre of mass of that circle. So I need to work out the individual centre of masses and areas. So I'm going to do my usual. My origin is there. So we could talk about kind of medians, halfways, 2/3 of the way along the median, but actually, if that's 0, I can just think of these as being the coordinates. The coordinates of the centre of mass for the triangle. The x coordinates, that would be 0, that would be 0, that would be 21 over 3. If I do the y values, that would be 0, that would be 0. This one would be 12. over 3. So the centre of mass of the triangle, 21 over 3, 7, 12 over 3, 4. I also need to work out the area of the triangle. Area of the triangle, it will be 6 times by 21. That's 126. Now if I work out the circle centre of mass, it's actually easier. It's just, of course, in the centre of that. From the diagram we can see that's 5 and that's 5. So the centre of mass is just at 5, 5. The area, it's a circle with radius 3, so pi times by 3 squared, 9 pi. So I think we best go down here for the table. So I've got my triangle shape, I've got my circle shape, and then I've got the total shape. My mass ratio. So we've got this pi in here, but I think pretty much everyone they're going to give you, there should still probably be a common factor. If I divide 126 by 9, oh, it's equal to 14. So I could, in my table, in fact I'm going to in my table, I'm going to write that as 14 and pi. So that's just a ninth of what it is to start with. So for my triangle, I've got my mass ratio of 14. I know that the coordinates are 7 and 4. For my circle, the mass ratio, I'm going to use pi, and my coordinates are centre of mass 5, 5. The total, so here, because it's a subtraction, isn't it? We've got a shape with a hole, so the total mass of my lamina with the hole in will be 14 minus pi. Centre of mass, we're going to say, is x bar, y bar. So this time, when I work out my masses times by my centre, so that's my triangle, I've now got to subtract because I've got a hole. It will be pi multiplied by 5, 5, and that is equal to 14 minus pi times by x bar, y bar. Should maybe put that in a bracket. And there's not too much we can do here, really, is there? We probably just have to go into decimals. I'll have, what will that be? 1798 minus 5 pi. 2856 minus 5 pi. 1 over 14 minus pi equals x bar. Oops, I've made it like a fraction. X bar, y bar. So 98 minus 5 pi over 14 minus pi. So I get the x bar is 7.58. If I now do the same on my other, I will have 56 minus 5 pi over 14 minus pi. Y bar is 3.71. So find the distance of the centre of mass of S from AB. So AB there, so that's going to be part 1, isn't it? That's the horizontal distance from BC, which is the base. So you get, that is my 3.71. Okay, and again, sorry, it's getting predictable, isn't it? We have got the angle between CB and the vertical. So here is my shape. There is my centre of mass. It's being hung for, oh, at least we're from a slightly different point here. So there we go. It's going to hang, it's going to hang, it's going to settle. That is my vertical there. So I'm going to draw that in. So my vertical, whoops, I've missed slightly. Vertical. I want to find the angle between the vertical and CB, which is this base here. There's my theta. I know that this is just my y bar distance, 3.71, but this distance here, I know it's 21 all the way, so that is going to be 21 minus 7.58, which was my vertical distance there, 13.42. So there's my triangle again. Here's theta, 3.71, 13.42. So tan theta, 3.71 over 13.42. Can we see that? Theta is 15 degrees. It wanted the nearest degree. Okay, so last one. Now the last one, I haven't got a plain old circle here, so we've got a uniform triangle lamina, a uniform semicircular lamina of the same material. Okay, so of course, if it's the same material, we know it's the same distance. So when we're working out our mass ratios, we don't need to do anything odd there. I know where my centre of mass is for the triangle. So let's do my triangle there. If I use my average of the coordinates, that is going to be my origin there. So the x coordinates are 0, 0, plus 12 over 3. And my y coordinates, 0, 18, and 18 over 3. So the centre of mass for the triangle is going to be 4, 18, 36, 12. Area is 6 18s, 9, I can do 9 12s easier. That's 108, yeah. So now looking at this thing here, I know where the centre of mass lies in the horizontal direction because of course it's symmetrical about there. So I've got 12 centimetres all the way, so it's just going to be there, isn't it, where the centre of the circle would be. However, to work out the vertical distance, so we know it's going to be somewhere up here, probably be a little bit further down, won't it? But this is where we have this result in particular here. So this was result that's in the formula booklet. You've got these on a little sheet. So a sector of a circle, of course, a semicircle is a sector. The radius are angle 2 pi, or sorry, angle 2 alpha. The distance of the centre from the centre of the circle is 2r sine alpha over 3 alpha. So whatever the angle is on your sector, you need to halve it to put in there. So we've got an angle of pi, so we're going to halve it to 2 pi. So this is for a sector with an angle 2 alpha and a radius r. The centre is 2r sine alpha over 3 alpha. It's on the formula sheet. We get to prove it after we've done a little bit of calculus with centres of masses in a couple of weeks' time. So here I know that r is 6, and I know that 2 alpha is pi, so alpha is pi over 2. So I know that my centre of mass is 2 times pi 6 multiplied by sine pi over 2, and of course sine pi over 2 is 1 over 3 times pi over 2. So 2 times 6 over 3, that's 4, but then we're dividing by a half, so it's going to be 8. We've still got this pi here, so 8 over pi. But of course what I have to remember is that this is just for this shape. I know from there to there it's 8 over pi, but using my coordinate system here, the centre of mass for the whole shape would actually have a y value, a vertical distance of 18 plus 8 over pi. I'm also going to need to have the area, so the area of that is equal to pi times by 6 squared over 2, 18 pi. So, my table, mass ratio, x and y, I've got my triangle, my semicircle, and then the total of the shape. So I could use 108 and 18, but there's going to be a clever factor here, isn't there? 108 over 18, divides in exactly. So I can just take that as pi, and I can take that as 6 18s, pi 18s. So I'll have my triangle with a mass ratio of 6, centre of mass 4 and 12. My circle, a mass ratio of pi, a centre of mass 12 in the x direction, and in the y direction, remember, it wasn't just 8 over pi, it was that 18 plus 8 over pi. Total mass 6 plus pi, 16, no, not 16, I'm not adding these. I need to find my x bar and my y bar. So, multiply 6 multiplied by the centre of mass, pi multiplied by the centre of mass, and 6 plus pi multiplied by this centre of mass. So I'm going to have 24 plus 12 pi, 72 plus 8 plus 18 pi, I think, yes. That's equal to 6 plus pi multiplied by x bar, y bar. So to find x bar, I need to divide 24 plus 12 pi by 6 plus pi. I think that gets me 4.69. Y bar is 80 plus 18 pi over 6 plus pi. That's 14.94. So that is, of course, from this point here. Part A, show that the centre, the distance from AD, yep, that's the way that I've done it. That's the 4.69. So that is part A. Part B, the centre of mass from BD, right? So BD is there. So I would just have to work out 18 minus that. Yes, okay. So I've worked out that the centre of mass up there is 14.94. So I would have to go there down to there. So from BD would be equal to 18 minus the 14.94, which gets me 13.3.06. Do we have to talk centimetres? Yes, we would, wouldn't we? Okay, and now the last bit is the dangling. So let's dangle it from where? Dangle it from B. B is here. The centre of mass is somewhere there. I know that this is my horizontal. I want the angle between that and BD. This is my line BD there. Just draw that out again. This is the angle that I need. I know this distance. That distance is this 3.06, isn't it? Because that's my line BD. This distance here, I worked out 4.69 was from there to there. So this distance here will be the total distance, 12 minus 4.69. 12 minus 4.69. 7.31. Again, it's tan. Tan of my angle is opposite 3.06 over 7.31. Theta is inverse tan of that 22.7, so that will be 23 degrees to the nearest degree.